everyone. Welcome to the Natural History Museum, our classroom here, otherwise known as our learning laboratory. Thank you for being here this evening. I'm Julie Van Sickle. I'm the director here at the museum, and we're super excited to be here this evening tonight with a wonderful presentation. I'm joined here by our assistant manager of the museum, Melinda Bailey, and our museum assistant lead, Copper, and Mark Bailey, our featured presenter here that we'll get to in just a moment. We're super excited to welcome all of you back here physically into our spaces after a couple of year hiatus. Late last spring, we were able to reopen the main part of our museum back to visitors for some limited summer hours, and shortly thereafter to some school visits. And we've been building back up and are very happy now. It's been quite the journey, but we're open to back our full 5 days a week with lots and lots of student employees and interns and volunteers doing lots and lots of things here at the museum. So it has been a real hub of activity. In fact, coming up here very soon on October 29th, we have a Discovery Day. Fun for the whole family. It's cool and creepy themed for fall fun and games for people of all ages. So we encourage you to come by and check that out. And particularly if you have any young people in your life, we have some little flyers in the back that you are welcome to take on your way out. We welcome you to all come back for that as well. So we have, this is our very first in-person lecture since March of 2020. So it's been a little while. We did some online things and those were terrific, but we're excited to be back here in person. So welcome to be our first group, and thank you, Mark, for volunteering to be this first one back for us. Appreciate that.
Someone's got to do it.
That's right. And we have a terrific presentation here for you this evening. We'll get to very shortly. But first, I wanted to take this opportunity to thank Melinda and Mark for all of their contributions to the museum over many years in the form of time and labor and love and generous financial support to really help a lot of what we do here at the museum. So thank you very much. I really appreciate it. And Melinda, as our assistant manager, coordinates this speaker series, and I will turn it over to her to do the introduction here.
So my one and only, in case you're wondering, Mark is my husband. And he started as a geologist after graduating from Chico State, which we found out some of our workers here from Chico, like Topper. So straight out of college, a geologist, hopped on things like oil rigs, went all the way up to the slopes of the northwest of Alaska. Big adventure there, worked for the Homestake Mining Company for a while, but then found out that, extraction wasn't his thing. Working for corporations wasn't his thing, so he went into education. He's a natural at it. So he became a science teacher, taught all grades, but high school was where he fit the best, liked the best. He's taught college classes, went back to Humboldt, got his master's degree in biology, not geology, transition in life, and did some Steve Sillett's first research student, got his master's degree. So he's a well-seasoned natural historian. Astronomy is his passion. But he's come back around to geology because he became the author of Chapter 3 in this newly published book, The Klamath Mountains, which really got him to focus back in geology, retired from the high school classroom, has taught on the side some OLLI classes from stone circles to astronomy to geology, and then here he is now for us. Who's going to take a journey through the geologic history of the Klamath Mountains, one of the places that we truly love. So.
Thank you, well, shucks. I'm going to give a disclaimer. I'm not an expert, but I've read a lot and I've walked these mountains a lot. I've done a lot of work in the Klamath Mountains, and if you can call pleasure and hours of just immersion in nature and just loving it, if you can call that word. So I was recruited by Michael Kaufman to write the chapter for this book because he knew I was a geologist, and whenever he came to our house, he saw my piles of rocks and I always collect rocks everywhere I go. And he said, "You're a natural for the chapter." I said, "Well, I don't really know much about the Klamath except, you know, some of the trails and some of the lakes and some of the rocks." And he goes, "You're our man." So instantly I said, "Well, yeah, I could use the challenge." So I dove into the literature and started reading and 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 reading, and it's just, there's so much. And what I learned almost immediately was it's super complex. The complexity of the Klamath Mountains is just beyond compare. Also, I love geology because I do like to learn about what happened before. I always liked this quote from Cicero: "Not to know what happened before you were born is to be a child forever." A rough translation of what he originally wrote in Latin. Cicero was a Roman senator, and he was an outspoken critic of Julius Caesar. And he paid the ultimate price for that. He chopped off his head and nailed his hands to the door of the Senate. So that's what happens to wise men sometimes in history. That was 43 BC. So this is what I was recruited for, this book. And there's all the chapters right there. I copied this just today off of their webpage. But the chapters are kind of scrambled up here. It's all the same chapters, but they're in different order. But as you can see, there's a lot of really cool stuff involved in the Klamath Mountains. And Michael and Justin decided they were going to pull it all together and produce the first natural history for popular consumption of the Klamath Mountains, just because no one had done it. Michael has a production company with his wife Allison, and they produce natural history books of really high quality. So I was delighted to be a part of it. There's illustrious former co-authors in there with me, and it's been a real pleasure to pull it all together. So what I'm going to show you tonight, how the mountains came to be, and this is generally a story of passage of time. Time is a real weird thing, but we'll get into that in a little bit. Deep time is what I like to call geologic time because it seems more representative of what it is. The farther back you go in time, it just has this depth to it that I find intoxicating. I just love the depth of time. And the more you look, the more you can get a feel for it, but you have to look to get a feel for it. It's not something that comes naturally. Then we'll look at the meat of the Klamath Mountains, the terrains. These are the large chunks that form various locations in these big arcuate paths, which we'll look at a little bit later. We'll look a little bit about the geologic maps of the Klamath Mountains. Phanerozoic highway road trip will take you on a little tour from Redding over to Eureka along Highway 299, which, as it turns out, is just a gorgeous cross-section of almost all the geology of the Klamath Mountains as you go across. One of the problems with that is there's not a whole lot of turnouts, so it's kind of scary to stop at some of these places. We'll look a little bit at the granite. I kind of think of it as the wilderness rock because I was really surprised when I started really studying the Klamath Mountains that granite isn't as large a thing in the Klamaths as I originally thought. Because going into the high country, that's where all the granite's exposed. So that's much of my past experience has been going into the high country in the Klamaths, and just seeing granite and granite and granite and granite. And so, but that's not really what the Klamaths actually are. Then we'll look at how the Klamaths rose and what little we know about how the mountains themselves that we see today originated. We'll look at the Ice Age and the Klamaths. And we'll look at the inevitable, I should say, exploitation and cultural survival that followed on that. Okay, so a quick look at geologic time. It's a tough concept. It's really hard to conceptualize. We normally think of time as, we think of it in terms of timelines, and I'm going to show you a couple timelines. But we think of it as a progression from one spot to the next, and we conceptualize it kind of as a line. But it's not really like that. It's a useful way of conceptualizing it. if you want to conceptualize something that you can't really put a good definition on. I mean, who in here has a good definition of time? I would challenge anyone to have an excellent definition of time. The best I've ever heard is a sequence of events. And God, it's kind of a boring description of time. Entire mountain ranges have come and gone, completely eroded away, including at the location of the Klamath Mountains. So the Klamath Mountains we see today aren't the first. Geologic time, of course, would begin, since it's geo-Earth, it would begin at the beginning of the Earth, and we now have a pretty good idea that the Earth was formed about 4.54 billion years ago. G for giga, or billion. Plus or minus 50 million. The oldest rock yet found, here's an example of it, found the Acosta gneiss up by the Great Slave Lake in Canada, 4.031 billion years old. I put an asterisk here because some say it's slightly younger, only 3.9. But so far, in terms of coherent rocks found where you could walk up and grab a chunk on Earth, the oldest place they found that's reasonably unchallenged is the Acosta gneiss. The oldest mineral grain yet found on Earth, found in Western Australia, is a single grain of sand in a sandstone that's 4.4 billion years old, a zircon crystal. We'll talk a little bit more about zircons. That's a crystal of zircon there. They normally don't get anywhere near that big. They're usually microscopic things. But they're a little bit tougher. They have a higher hardness than quartz does. So when you're looking at sand that's eroded from mountain ranges by rivers and streams and such, oftentimes that sand is made almost exclusively of quartz and zircon because they're really hard and they last. They're survivor mineral grains. A little bit more on that later. So the oldest rock yet found in the Klamath is just a little over 1 billion years old. But if you think about it, a billion years, whew, that's a long stretch of time back. But the Earth had already been around for 3.5 billion years by that time. So it's hard to imagine this far back being kind of relatively little consequence compared to the overall age of the Earth. But in the Klamath, that's pretty much old, but that's not as old as it gets. Again, the old trusty zircons. 3.2 billion years, one has been dated, a single grain over sandstone. So what this means is most of the rocks of the Klamath, when we look at an actual cobble in our hand or something, they're much, much younger than this. But if they're a sedimentary rock, they're going to have grains in there that are potentially really old. So keep in mind that if you have a sedimentary rock, all that material has come from previously existing rocks, which might have themselves have been sedimentary rocks from previously existing rocks and so on. And it's the zircons that can survive that sort of erosion, making it a sedimentary rock, re-eroding, making it a new sedimentary rock. They can survive several cycles of this and still be intact and recognizable. So if we're looking at the geologic time scale, as geologists have worked upon, this is a sort of a confusing but very instructive for a geologist, geologic time scale. Geologic Society of America has done this. They update it periodically. And all of these names in here they've given to based upon rocks that they found all over the world of various ages. This represents an immense amount of effort from thousands and thousands of scientists working in the field, all pooling their knowledge, adding to the literature, and others reading that literature and building it bigger and bigger and bigger and bigger. So we could never do something like this. We could never figure out geologic time if we didn't have writing, because it's the work of our predecessors that allow us to pool all this together. Some people kind of like this illustrated in this form. In a way, it's kind of more pleasing, but it's a little bit less familiar because we are kind of thinking of time as linear. But you can see that these earlier sections, we're talking about 2 billion, 2.5 billion years here, 2 billion, 1 billion. Much of the action in the Klamath Mountains doesn't even start until in here. So a lot has happened on Earth long before the Klamath came along. So take a moment to look at this. This is another way of looking at the geologic time scale, going from the Precambrian to Paleozoic, Mesozoic, Cenozoic, today, right here, somewhere within the pixels of this line is today. And in the colors are the names of the different terrains, which we'll describe in a minute, in the Klamath Mountains. And the black text is significant events that have happened throughout that time. So if we look over here, for instance, at some of the earlier subterraneans, these are all, as you can see here, the eastern Klamath terrain. That includes all these red things, the subterraneans as well. So there's a lot of subdivisions amongst these. But some of the oldest ones, the Wairika subterranean and the Trinity subterranean, are pretty interesting. And we'll look into that in a minute. But you can see that from those, you can see what's happening. The oldest Klamath rock, mineral grains are in there, Cambrian explosion. Lots was really happening on Earth while this was going on. Rise of the fishes, that was still happening. It was hundreds of millions of years afterwards, but it's still part of the eastern Klamath terrain. And then some of the things you might have heard of in basic geology classes, Pangea and stuff, you think of this as a super, super ancient thing, which it is. And yet, look at it here, it's a lot has passed before that even happened. So perhaps a more familiar way to look at it would be like this. So we have the Precambrian, which they break down into the Hadean, Archean, and Proterozoic, before the modern time, Phanerozoic. And again, remember, we're right over here within that line. So much of the Klamath action has happened in this area here. So this isn't a particularly useful thing. It gives you a little entertainment in seeing what's happened in the past, but it's not very accurate in its graphicness. So this might be a more accurate timeline in terms of what's happened on Earth. Here's everything that's happened before all of this. So the things that, the events that have produced rocks and fossils and zircon crystals and stuff that we recognize today are largely recognizable because the rocks survive that we can see. And most of what's happened before the Phanerozoic, there's very few rocks on Earth that survive, for reasons we'll get into in a little bit. So most of the Earth history, there's very little representative rock material from that. And to find those, you have to go to strange, faraway places like north central Canada and Western Australia. Those are a couple of big places that have some of the oldest rocks. So here's another way of looking at it. Here's the entirety of geologic time. Here's the Phanerozoic, dinosaurs and stuff were in here. Then we expand this section out to here. Much of the Klamath Mountains are through this area right here. Again, we're right over here in this line. All of the kind of familiar stuff to us in terms of modern day life forms are from the Cenozoic. Here's the Cenozoic expanded out. We have lots of subdivisions within those. And almost all these subdivisions are based upon fossil evidence that they find. And back in the day, before they could do radiometric dating and tell an absolute age for rocks, they had to go strictly on fossils. And so they would look at fossils all over the world, and they would see, seeing a fossil here, and it's in the rock layers below a fossil here, and which is in the rock layer below that. When you accumulate all the people's observations, the pattern starts emerging that there's things that came definitely before other things. So it took centuries, basically, to come up with this plan. And then lastly, the Quaternary. This is when, if you went back to the early Quaternary, this is when you would recognize things as common, the types of things you see today. Maybe not the same species, but closely related, and in some cases some of the same species. So when we're looking at geologic time in its entirety, what we think of as very long periods of time, like for instance the Quaternary, are actually pretty brief intervals. I like this one, so I threw it in just for the fun of it. This shows different organisms and their proportions, how much of all the life forms in the vertical axis were each of these different kinds of things at different times in the geologic timeline. And notice this, this was like prime dinosaur time. That's when the flowers first started emerging. And now angiosperms, flowering plants, are one of the dominant types of vegetation on the planet. And so almost everything alive in terms of plants are angiosperms nowadays. And many of these things like cycads, there are only a couple representatives on the planet now, and they used to be pretty common. And ginkgophytes, virtually gone. Conifers, they've held their own pretty much in terms of overall proportion based upon the vertical thickness of these bars. So things have changed quite a bit. There's been other things that have completely disappeared. Luck of the draw. Sometimes asteroid impact, sometimes massive volcanic eruptions would change climate enough, either of those two, would change climate enough to eliminate it. And we're only here because we got lucky and our mammalian ancestors just happened to be burrowers and could be underground when the Earth heated up to peak to oven temperatures on the asteroid impact that killed off the dinosaurs and opened a pathway for us. So it was a disaster for life on Earth when the asteroid hit that killed the dinosaurs. But it was our big chance, and we rose up and here we are. So, much of the dating that we get when we look at time in the geologic scale is from the mineral zircon. It's zirconium silicate. It can be a gemstone when you find it big enough and if it's pure enough. And with many of these minerals, with many of all minerals, they're usually just kind of cruddy old things that don't facet up and polish nicely like this. But some zirconium silicate can be beautiful. These are all different colors of the same thing. So if you're thinking that minerals have a specific color, they don't. They have a lot of different colors, most of them. There are a few minerals that have just one color, but many of them have a wide variety. And this is how they look in the rough before they're faceted up and stuff. These obviously would not be good stones to make something like that out of, but maybe these. So zirconium silicate is probably my favorite mineral because it's so informative, it's so durable, and it lasts so long that, and it's just packed full of information about timescales. It can be readily dated because there's uranium sometimes mixed in the crystal lattice with it that decays to lead, and you can get the uranium-lead proportions and work out an actual date for the age of formation for that crystal pretty easily. I know graduate students who do this all the time. It used to be a huge thing, you have to have vast labs and stuff to do it, but now graduate students can do it routinely and find the age of zircon crystals. So, another cool thing about it is the blue. I put this in blue here because that's the zircon in the center of these little triangles of blue. The green parts are the silicate tetrahedra. And so it's not just those. Sometimes there's other trace elements like the uranium I mentioned and others too that give a very specific fingerprint to a particular zircon crystal. And the interesting thing about it is each location where these zircon crystals form have a unique chemistry. The melts that they crystallize from are unique chemically. And we've gotten to the point now where we can actually count individual atoms and look at the proportion of all of these foreign, we'll say, elements in these crystal structures. And this proportion gives a location, it's a fingerprint, and we can tell where the crystal came from. And we'll come back to that in a minute because that works out to be pretty cool in the planets. So this is what they call an accessory mineral. It's not a major rock forming mineral, it's just a little mineral bit here and there in other rocks. But like I mentioned earlier, it's harder than quartz, so when the rock that it was formed in disintegrates from erosion and weathering, the zircons survive. So it's incredibly persistent. And it's a common component of sand. You don't normally see this, you think of sand as sand, just grains of stuff. But if you get a magnifying glass, go out to the beach and grab a handful on a sunny day, look at it under a magnifying glass, and it's pretty interesting what's there. Largely quartz, but there's a lot of zircon mixed in there with them, and almost any sand that they've got. And interestingly, we also find zircon in lunar rocks, rocks on the moon, rocks on Mars, meteorites. It's ubiquitous everywhere where minerals form, where you get a large parent body forming minerals. So this is like one of those things where, wow, this is not unique to the Klamath, it's not unique to Earth, it's not even unique to the solar system because the chemistry is the same throughout the universe. So there's zircons across the universe, and across the universe they can tell us the same thing, but we just can't get our hands on those. Oh, okay, so outcrops are where geologists go to find these zircons and all the rest that we're going to see tonight. This is up by Happy Camp. These exposures, called outcrops, are where magnet-like geologists go to find out what the flavor of the ground is, so to speak. And these are all, this kind of gives you a little idea about the complexity and the difficulty of figuring out what's going on in the Klamath, because, you know, it just looks like old cruddy old ground, you know. But if you look at it closely, there's a message there. And if you look at it even closer, the story emerges, which is really cool. So these are pictures throughout the Klamath of the various rock types. And to the average person who doesn't have any geology at all, they just pass right by it and don't even realize that there's volumes of Earth history information in all of these outcrops. You might recognize this location. And so throughout the Klamath, as we drive down the road, we encounter different kind of rock, different kind of rock, different kind of rock, different kind of rock. But as we examine them more closely, we find that there's distinctive patterns to that. This is up along the Salmon River. And this is the best kind of place when you're in steep mountains to look for rock outcrops, is where there's road cuts, because usually you get a nice, fresh, clean cut with not much vegetation on it, or in stream cuts, which are a little harder to deal with. That's why one of the reasons why deserts are such good places for geology. When I was a geology student, that's where we went for field camp, was the desert, because there's no vegetation. The rock is just right there everywhere you go. And you can look across the valley and see all the rock and see all the layers all stacked up next to each other. And at a glance tell a lot about the Earth history. So here's a sampling of some of the rocks I've picked up around the Klamath. I tend to go out and look for the more interesting things. You might notice that I'm not putting too many just, well, maybe you don't notice, but you might notice I'm not putting too many just blah rocks in there. Because, you know, the pretty ones are cool. This one is maybe the most blah of all of them. It's really a cruddy rock. That came from over near Reading. So there are good rocks and there are bad rocks. This is a good rock. That's a bad rock. Sort of. Okay. So now let's look at the bigger picture for a minute and see how the Klamath Mountains would come together from all this. So hopefully, how many of you know something about plate tectonics? Okay, something. Yeah. What a plate is and all that. Oh, okay, maybe happy. So I'll go through this as fast as I can. Hopefully it won't blow you out of the water. So the Earth is the surface of the Earth, the crust of the Earth, like the peel of an orange, is broken up into a bunch of segments, and they call those tectonic plates. and they shift and move in relation to each other. And along these boundaries, wherever there's a boundary, there's a mountain or a mountain range, particularly where plates converge and come together. So we're up here, this plate, the Pacific plate, is pushing in largely up in here and all around here, underneath the adjoining plates. And interesting things happen. Whenever you get rocks coming together, you get rocks twisting and gnarling and pushing and crunching and earthquakes and volcanoes and lots of really dynamic stuff going on. Where you get plates coming apart, like it happens here, rock bubbles up from below as lava. It's usually under the sea, so we don't normally see those. But the largest mountain range on Earth is a mountain range formed by lava coming up along these diverging plate boundaries that are almost entirely underwater. In a few places, like Iceland, it pops out at the surface. But mostly, this largest mountain range on the Earth, kind of like the stitching on a baseball, is largely hidden below the ocean. So we have three different types of plate boundaries. The ones most important to us are these two right here. We get two boundaries sliding next to each other, a transform fault boundary, and the plane between those sliding past each other is a fault, what they call a transform fault. And the San Andreas fault is a classic example of that. But the San Andreas doesn't participate in the Klamath Mountains. A converging plate boundary is when this plate and this plate come towards each other. And something gives when that happens. Usually what happens is one plate dives underneath the other or subducts. So this is what we would call a subducting plate. And when this happens, it's pretty cool, but with major consequences for the Klamath. But that wouldn't happen without these divergent plates somewhere out in the ocean, because as the lava bubbles up along this crack in between them, it pushes the plates away. And in process, it's also forming new plate as it goes along. So lots of interesting things happen there. Like for instance, as the plate dives, it gets deeper and deeper, and hotter, and it starts melting and bubbling up to the surface, and you get volcanoes happening here. Volcanoes are central to the whole Klamath story. Even if you don't see volcanic rocks, they're still central to the whole Klamath story. And the reason being, we'll just look at this one type of boundary now, is because all the rocks that we find in the Klamath are associated with this sort of boundary. We get the bubbling up things, and if they don't come all the way to the surface, they form these big bodies called plutons of rocks like granite, things you've heard of and seen and enjoyed looking out there, the salt and pepper crystally rocks. But important to the Klamath are the rocks right here, the muds and stuff that are scraped off of the plate as it dives down underneath. It's kind of like scraping your boots on a boot scraper before you go in the house, scraping the mud off of them. And because literally it is mud getting scraped off. Much of the stuff gets dragged down and disappears, is melted and out of the picture. But some of it, small portions of it, glom on and get stuck on that and build the plate, this plate, bigger and bigger. In the case of the Klamath, not right now, but much of the past of the Klamath, the rock-forming parts of the Klamath history, it was a situation like this, where we get what they call a magmatic arc. Volcanic island arcs where these bubbles popped up, much of it coming through the surface, exploding as volcanoes at the surface. And the plates, when they collide, tend to form these arc shapes. So they call them magmatic arcs. And there's the fore-arc region, the ocean-directed region, and sometimes there's a back arc basin that has water in it. And both of these kinds of rocks are represented in the Klamath. And as these mountains popped up in the Klamath distant past, they start eroding immediately. As soon as you get a rock above sea level, it starts eroding. And it sheds sediment off in both directions. And the types of sediments can tell us that this is going on. In fact, it is the sediments that have told us that this is going on. Because when we look at the sediments that have spilled off this, they're the types of volcanic rock sediments that are formed in this kind of situation today. So we go to Japan, the Philippines, Aleutian Islands. These are all analogous structures that are going on today. Like this. Here's an island arc system. And they'd pop off just like this one seen from space. On and on and on for hundreds of millions of years this has been going on in the region of the Klamath. So way back when, 100 million, 200 million, 300 million, 400 million years ago, lots of what was happening offshore in western North America, where the Klamaths are today, was this sort of thing. So we can tell this from the sediments that were shed off, and you can walk up on these road cuts, chip it off. A geologist could take a piece off, look at it under a microscope and say, that's island arc rock. And they could do that because they look at modern day analogies, and you can see, oh, that's the same stuff. So it's pretty rock solid, so to speak. So the Klamaths then are made up of these boot scrapings, kind of, glommed on bits and a bit at a time, and we call these things terrains. Sometimes they're referred to as exotic terrains, but they've mostly just shortened it to terrain. And so these are island arcs, for instance, that are popping up out there in the ocean and cemented to this diving plate. Most of it gets subducted down and disappears, but parts of it, and for the Klamath geologist, a disturbingly small part, gets glommed on, but it's enough to be able to tell what's going on with very careful study. So eventually, you get these things sutured on, like it shows here, onto the continent. The continent grows wider and wider and wider. And every time you get these things sutured on, like here where the suture is, there's compressional forces, and they form these thrust faults. If you push blocks of rock together with too much pressure, they're going to snap. And they usually snap along these so-called thrust faults, where one block overrides the other. So it turns out in the Klamath Mountains, all of the terrain is separated by thrust faults like this. And that's how we define, in part, these terrains. So if we look at all of western North America, here's the Klamath Mountains here. Seem pretty big from our perspective, but from the western North America perspective, it's a small part of a much bigger picture. But all of this stuff is accreted terrains. So the whole of western North America, from Central America all the way up into Alaska, and many other places on the earth, form in the same way. And this is millions of years of accumulation, glomming on. This is extremely simplified vision of what has been happening. So, we only represent kind of a smaller section. And this happens all over the world. So if we take this section and expand it up to this, here we are in the Klamath Mountains. This extremely simplified version of the terrains of the Klamath Mountains. We get the eastern Klamath terrains, which are themselves subdivided into several things that you might remember from that chart earlier on. The western Klamath terrain and everything in between. Now, if these things are getting glommed on one at a time, as the plate comes in and smashes onto the North America, which side, this side or this side, do you think would be the oldest rocks? Oldest rocks on the right or the left?
Right.
Right, yeah. That's exactly what happens. So when you drive from Reading on 299 across here, the rocks get younger and younger and younger and younger. So it's, in some ways, it's a nice clean system. It works really well, and it largely works until you start looking at the detail. And then it's just devilish detail. And there's all kinds of contradictions, but the general picture, though, is so far correct. So let's take our simplified version and look at a real geologic map of the same area. Each color representing a different kind of rock. The dark reds, for instance, are granitic rocks, and you can see from that, and the pinks are also granitic. You can see from that most of this is not granitic rock, most of it is other. Believe it or not, this is a highly simplified map. If we were to take a section of this, and a guy named Porter Irwin put all this together from previous geologic maps that he and other people made. So they'd go and take a small little section of this, like maybe a 1 mile section, and they'd map it in detail, just horrendous detail that looked much more complicated than this. He took, and then they filled out this whole map area with such maps. And Irwin took all these maps for the first time in 1969 and melded them all together into a comprehensive map of all the Klamath Mountains. Now this just happened since 1969. We didn't have the picture at all before then. It was all fragmentary information that we had. And Porter Irwin showed that this all had a pattern and that it told the whole story if you knew how to look at it. So let's go back to this one again and overlay that. That's the same spot. So there's a lot of really interesting stuff going on here. The black lines are the surface points where those thrust faults that I mentioned come out of the surface. So they're also the boundary lines between the different terrains. And then these granitic outcrops in the reds and pinks barge their way up through all that after it was already made. Keeping in mind all this is happening just in this wedge right up in here of this overall time scale. So we're talking about whole mountain ranges coming and going again, all in this little tiny wedge of geologic time. Question?
Yeah, I mean, I don't know if you want to take questions now or what, but
Yeah, just go for it.
Okay, I'm just a little puzzled about how the accretions are so varied. I mean, if the model is that they get sutured on to the plate as it gets subducted, and there's this thrust fault happening, but where does the variety of rock come from? You'd think that, you know, if it's just one plate subducting under another, there might be similar material that...
Right. And you would think so too, but when you look at all the different rock types that can form in an environment like that, for instance, on one side of that island arc in the four-arc basin, you'll get calm water sediments. On the other side, you might get deep water sediments. And furthermore, you might get some undersea lavas popping up underneath there. You might get deeper rocks that when they're glommed onto there and then the whole thing raises up and they're eroded and exposed, you get a whole different suite of different kinds of rock that way too.
Yeah.
So and then on top of all that, all this pressure of converging stuff, miles and miles, 100,000 feet of rock scrunching up together, that causes them all to mineralogically change into metamorphic rocks. Here, more so here than there. And so you end up with this, from basically a few kinds of rock, you end up with this hodgepodge of changed, metamorphosed, unmetamorphosed, twisted, tilted, turned, jumbled rock. It's just unbelievably complex. And it took them years to find this out. In fact, the whole terrain model kind of got its feet on the ground and started running from studying the Klamath Mountains. Then they started realizing same thing's happening in Alaska, same thing's happening in Mexico, same thing's happening in Panama. It's really weird. So, all this was kind of what happened once these rocks started forming offshore as individual terrains, and I'll show you a few pictures pretty soon. There's multiple arcs offshore moving in, these terrains coming in. This was part of what we call the Nevada orogeny, which was a sequence of making, orogeny, by the way, means mountain building event. And Nevadan, based upon the fact that they first started discovering, and they first started dawning on them that this orogeny had occurred when they were doing work in Nevada. They always put the first name of the place where they first came up with the idea as part of the name. Okay, so this was all part of the Nevadan orogeny. So this is a picture of the western Hayfork terrain. It's a meta-andesite, which means it's an island arc andesitic lava that has been metamorphosed, or complicated, making it difficult to figure out. So this happened in the late Jurassic, which was kind of dinosaur times. But by only 140 million years ago, most of this island arc volcanism had ended. So most of the rocks in the Klamaths are, the youngest are about 140 million, and the oldest go quite a bit further back from that. So by this time the terrains had largely finished forming. And what did it look like where the Klamaths are? No one knows. because all of that eroded down to the roots and went away, and the seas got closer in further to the east, and then it rose up again in another activity, and the sea pushed further towards us now, more erosion happened. So on top of all that, not only do we have this complex churning of rock, but it's being distorted, washed away, largely obliterated in most parts. Pretty strange. So here's what you have to face when you're out there looking at this. You just look at these kind of cruddy looking bad rocks. They're not the charming rock that you want to put on your mantelpiece. But they're the ones that are loaded with all this information. Another really cool one, can't quite see it in this picture, all these protrudences here are pillow lavas, indicating basalt that has flowed out under the ocean. And this is up on the Salmon River, South Fork of the Salmon River. Pretty far inland, pretty good elevation, long ways from the ocean. If you look really close, this is a pretty good representation of the kinds of chaos that happens to rocks. From simple rocks, like a simple volcanic lava piece, like if you go to Mount Lassen and stop on the roadside and pick up any old rock, that's a pretty simple, unmetamorphosed, straightforward, modern volcanic rock. And that's what a lot of this was, back before it was stretched by these pushing plates together and the churning pressures and temperatures. It just reshapes and reforms all this stuff. So the specialists can look at these and identify what they once were. They do lab experiments that take rocks and put them under extremely high pressure and extremely high temperatures and see what happens and see what they become. Okay, so we won't dwell on this too much, but this is all of the terrains over here that we have in the Klamath and subterranes here. Their approximate ages and a brief description of what they are. And if you look closely, most of these are this jumble of a bunch of different kinds of rock, and you have to ask, how the hell can they separate that from all the other terrains? Well, it comes back to those thrust faults again, because those thrust faults separate the individual terrains. In part, it comes to that. But it also comes in part, there's subtle and not so subtle differences in a lot of these that allow you to see, well, that's definitely different than what I was seeing over in the other valley, across this other side of the thrust fault. But you can also see that the ages on these things are sort of all over the place. It's not a nice, easy, oldest down here, younger. There's a lot of age range in these. But the general trend is, you can see down here, 400 million years to 130, 137. So a definite decrease in age there. So just to come back to this and just show you, just to remember, these different colors indicate that these terrains formed at very specific times. But the most recent one is right around 140 million years ago. Okay, so now, we'll take a road trip. The Phanerozoic Highway. Let's start on the eastern Klamath terrain, the oldest of the oldest. Wairika subterrane is the oldest. This formed in the Precambrian in an era of time that they call the Ediacaran. And this is a really, really cool time in fossil life, because this is when the first multicellular animals and plants and such, let me back up, the first multicellular organism started showing up in the fossil record. There was an explosion of biodiversity, multicellular organisms just appeared. So nothing like this had ever happened before. And we have representative rocks of this in the Klamath. This is what the Earth looked like at that time. The Klamaths were would become somewhere out here. And there was a big supercontinent called Rodinia that has since, you can see it starting to split up here. It broke apart and the plates shifted all over the ocean, like it's been doing all along. What they found are these cyclomedusoids in Antelope Mountain over by Wairika. And what are cyclomedusoids? Who knows? They're these weird round things. Here's a picture from paper, Lindsay and Griffin, that I got some really cool information from. These are the rocks. They're round things, and they have no idea what they really are. There's no modern day analog to this. So were they an early animal? Were they an early kind of jellyfish-like thing? Were they fungus? We don't know. But they didn't last for long. And they are represented in the Klamath rocks, but only in a very specific spot, and it's on private land. Then we'll move into the Cambrian period. Really cool Anomalocaris, they call that guy. Really cool, weird creatures swimming around. The Cambrian period started in 541 million years ago. And the best location for that is up in the Canadian Rockies, the Burgess Shale. You might have heard of that. And it's a pretty famous fossil site. This is when the first explosion of animals, the best exposure of the first animals started showing up. And the Klamath Mountains at that time were out there, non-existent. But the sediments were existent, and they were accumulated. And we can tell from the direction of the sediments, you can tell in subtle cues in the rocks themselves what direction the sediments were deposited from. And they were obviously deposited from land, so we know that there was a large landmass off to the east someplace. And so again, and if you're interested in this, I got this from a thing called Earth Viewer. It's a cool little app that's really fun to play with, and it's pretty accurate. This is accumulation of centuries, essentially, of people putting bits and bits and bits of piece of the puzzle together, and finally a big picture starts emerging. And we're getting pretty darn accurate with it now. So the Wairika and Trinity subterraneans of the eastern Klamath developed during this time frame. And so here is a cross-section across Highway 299, and super simplified. But you can see, the names of these things. I'll expect you to regurgitate these in the test at the end of the class. But there's a lot of stuff in there, but there's a lot more in real life if you're out there chipping around with a rock hammer. But there's a pattern that is simplifiable, put it that way. Okay, and then we move to 365 million years ago, only 365 million years ago. Late Devonian, this was the age of the fishes, and all the fishes were heavily armored, which tells you something about life around these fishes. They had to be armored to survive. Okay, so the Redding subterrane, a part of the eastern Klamath terrain, and the central metamorphic terrain developed during this time period. And this is what the Earth looked like at that time. So you can see the United States superimposed of today, superimposed over there. Here's Nevada, California would have been here. So these would be the terrains that you would find out in Nevada, modern day Nevada. But the world would be unrecognizable. But it was largely kind of shallow sea off to the east, kind of perfect environment for lots of weird organisms that you see in museums and stuff to form. And the perfect environment for them to be preserved too, because they would die, they'd fall down, get buried, especially from sediments spilling off from rivers flowing out into the ocean. They'd get buried rapidly. They'd have to be buried rapidly or they'd be eaten. And then you got to get lucky enough to get to a spot where that old rock has been pushed up and exposed by new erosion at the surface, and then you have to be lucky enough to be walking along. Then you have to be lucky enough to be able to have the eye enough to see some of these fossils, because some of them are super subtle. Fossil hunters definitely have an eye. They're not just regular people that are out scratching around. They're out with a mission, and they know how to look. The Redding subterrane, one of my favorite parts of it is a unit called the McLeod limestone. And this is the McLeod arm of Lake Shasta. The McLeod River used to be right underneath there. In fact, it is right now, right there. Last time we went by there, this is a river now, it's no longer a lake. So that's sort of scary. And the same thing, by the way, is true for Trinity Lake. It's now the Trinity River and no longer Trinity Lake. But over in this area over here, there's a really cool cave, which we'll talk about in a minute. So here we are on our highway map. We're located at this location. And then looking down the McLeod River. This is all limestone. And if you look at limestone, limestone comes from one thing. and that's the limey sediment that gets deposited at the bottom of semi-tropical or tropical seas. So this tells us right off the bat it was tropical, and when we look more closely, there's corals in it, and an extinct type of coral too. These guys, horn corals. There are no horn corals on Earth anymore. So there are these weird kind of horn-shaped corals that would attach to the bottom. And in each an individual animal, they grow a new layer, kind of like a tree ring every year. But they're gone. Don't know exactly why they left, but they're not with us anymore. But there's certainly lots of coral of other types today, for the time being. And then, quite a bit younger, look at this. Here we're talking 350 million years. And this is still considered the eastern Klamath terrain more than 100 million years later. So some of these terrains are a lot of stuff spanning a lot of period of time, but they fit together for reasons that we don't have time to get into. But at that time, here we are out in western North America, and now you can start to see how these terrains would be out there. So they found some really cool stuff in this Hasselkuss limestone. And apparently you could go over there. I haven't done it yet because every time I want to do it, it's 150 degrees over there. But there's some public lands where you can go and chisel away on these rocks and find these fossil reptiles. And they have interesting names like Shastasaurus and Californosaurus, Ichthyosaurus. And here's a V for a scale to show how big they were. Some were quite a bit bigger than that. Okay, then central metamorphic terrain was formed, again, in a wide range of time interval. And these are previous rocks. This is made entirely of the salmon schist and the Abrams schist. And these were formed from sedimentary and volcanic rocks that have been squeezed, pushed, crunched, rearranged in their atoms into new molecular forms. Right there at this spot. North Fork terrain. Late Paleozoic. At this time there were some large glaciers in there. That's when these guys hung out. And where we're at, you wouldn't have seen this because it was largely open ocean, but there'd be the occasional volcanic arc island out there. But mostly marine organisms are what we find when we look in the Klamath because it was largely a marine environment and not at all terrestrial. But on land there was a lot of interesting stuff going on. So here's a good example. This is a limestone outcrop. You might recognize this. This is just short of Junction City. And limestone is one of those tough rocks. It's just kind of this gray, hard, nondescript kind of rock, unless it's loaded with fossils. And almost any limestone, if you saw a nice smooth cut and look at it under a microscope, you're going to see fossil organisms in it, which tells us that limestone does form from the debris of living organisms. That's there on the map. So, let's talk about ophiolite sequence for a moment. These are a sequence of rocks, and they're common all over the world. This is what forms on the ocean bottom, and all the sediments stack up on top of that, deep marine sediments on top of that. So if you dig down through those deep marine sediments, you find the pillow lavas that erupted where the plates are coming apart, adding new material onto each side of this split and making a plate as it goes. And as that plate is made, sediments land on top of it so it gets buried by them. But if you go down deeper, you get the so-called sheet dikes, and then underneath that is gabbro, and then underneath it is peridotite. And all this stuff can be metamorphosed into serpentinite, which is everyone's favorite rock, at least mine. And these are all rocks from the Klamath, and these fit into the perfect ophiolite sequence. And as it turns out, the ophiolite sequence that you find, there's several of them that we find in the Klamath. So one of them is the best preserved one on Earth, and that's in the Smith River area. And they're in purple. So all the purple here is where remnants of these ophiolites happen. And the bigger the remnant, the more complete that sequence is. And it's always the same. So it's now known, and we've drilled down through these from drilling ships and confirmed it. It's now known that that's the standard sequence for what you would find on the seafloor. So when you see it high up in the mountains in the Klamath, you know that this was below the ocean at some point in the past. It's the classic signature for that, which is really cool. Moving down the highway towards us, eastern hayfork terrain. Now, the eastern hayfork terrain, while it was being laid down, this is the kind of stuff that was going on in land. A strange world. All the plants would be odd if we went back in time. Lots of flesh-eating, human-eating dinosaurs. It's not the kind of place you'd want to go back in time to for very long. You'd want to have an armored suit or a tall tower or something like that. But where the Klamaths were, this is what the kind of organisms that were living there at that time. And we occasionally find these guys, ammonites, highly distorted in these limestone deposits. The limestone is largely obliterated by the subduction, and just little bits of it have survived. And those that have survived have twisted and turned, and so these are kind of distorted, and they're not common, but they have been found, and that helps to age date them. So in places like this is along Highway 299, layered sediments of this eastern hayfork terrain. But largely, it's made of sediments called melange. And melange is a geologic term that they use that means sediment that has formed by undersea mud flows and landslides. So it's just this jumble of everything that slides down the undersea slope and jumbles up together, and this happens again and again and again and again. It's happening probably this instant right offshore out here. To become some future geologist, a rat geologist in the future, will be scratching their head over the melange that's forming offshore right now. This one, because that melange is such a jumble, it's highly prone to slides. And this big slide, the Big French Creek slide, slid off and closed Highway 299 intermittently for months back in 2018. That's right there near Junction City. The western hayfork terrain, a little bit younger, but still quite a range, 20 million years. It's starting to look kind of like North America, but it's still almost completely connected to Africa and South America at this time, with just some small opening seaways, kind of like the Red Sea happening there. And here's a typical outcrop of that. These are sediments made largely of andesites from offshore volcanoes. And then the Rattlesnake Creek terrain, this has a huge range in here, and they found some boulders in there that are much older, apparently rolled down from some nearby mountain made of older rocks. And it's mostly sort of bad rock, you know, cruddy old rock. I just say this in jest because all rocks are good rocks. The western Klamath terrain comes next. Also quite a range, but you know, we're getting sort of a more manageable size of 50 million years. The Smith River subterrane is one of the more interesting ones because it has the so-called Josephine ophiolite. And this is what an ophiolite looks like at a glance. It's not those nice distinct layers, but those layers have been pushed and twisted and jumbled, so it's just kind of like, you know, a hodgepodge. But if you look closely, you see all of those characteristic rocks. And they typically weather orange like this. So they don't look orange in a fresh, broken face, but when they've been exposed to the air for a long time or exposed to near surface water, they oxidize and become red like that. And then sitting on top of that is the Galice Formation, which is what you see going up to Orleans and so on. There's a lot of this around in the western Klamath terrain. So just a quick reminder, the Josephine ophiolite is your typical ophiolite, and it has all these typical rocks. And in fact, all these pictures, but this one came from the Josephine ophiolite. The rocks. And then we leave the Klamath Mountains. And this is just this side of Willow Creek. And there's this serpentine area. And whenever you see serpentine, it's usually indicative of a fault there where rocks have squeezed up and oozed up and converted into serpentine in the process. So it's a broad area through there where there's a thrust fault, and then from that point on is the Franciscan Formation of the Coast Ranges. And those are all made of sediments that came from the Klamath Mountains, the ancestral Klamath Mountains themselves washed out while they eroded out to sea, got compressed, and became what we call the Franciscan Formation. Okay, so that's our tour down there. So this is a quick little rotation. This is how, I notice the different colored terrains on here. We're going, look at the ages here as we go through. We have found through magnetic studies that the whole thing has rotated around from this position to this position to this position to this position. This whole thing has been shifting throughout the whole history of the thing and to where we're at now. And has it just been the Klamath Mountains themselves that have been twisting like the dials on a clock? No, some of the terrains themselves twisted like that, but it's probably the whole continent has been shifting along that, like that, as all of the plates shift and move and grind against each other on a global scale. So when we're looking at this, we're looking at sort of a global phenomenon. So watch this. This is the past billion years, and these are continental land masses, and this is how they've moved. So far, 800 million years ago, nothing that's recognizably North America is here yet. So there's a lot of scrunching, crunching, twisting, changing kind of.
This is sequential?
Yes. And this is hard field work that people have put together. Now we get North America starting to show up. Sort of. This is hard field work that people have labored over and scratched their heads and published and published and published and absorbed and re-field work, and this has been quite a spot.
That animation was, I think I saw it online it was only last year.
Yeah, that came out just last year. So that was a very modern accumulation of all this.
Parker, just let
all
you
this
know
information.
you're over time a little bit.
Okay, I'm almost done. Okay, so I'll skip through this part really quick. The plutonic rocks, we already talked a little bit about that. We'll just say the plutons are subdivided. They're just large chunks of volcanic rock, and you see things like this at Gibson Peak in the Klamath. And there's a map showing in color where all of the plutons are in yellows, greens, and pinks and reds. So you can see the bulk of the rocks aren't of that type. But they're all distinctly aged, and as they pop up through, since you can age these things, anything that pops up through something is younger than what is popping up through. So you can tell that you can build up a sequence of events of what happened when by how these different aged plutons have popped up through it. And here's a sequence of plutons that have been popping up through over the years by different ages. And there they are. And here's some famous ones. Okay, now, I'm going to try to, as you can tell, this is hard to do in a short period of time. This is so complicated, and it's really hard to simplify it enough to where non-geologists can kind of get a handle on it. And I'm sure I'm going over a lot of your heads just because it's so much. But how old are the Klamaths? Well, we don't really know. If we go back to the Eocene, this time period, we know that there was mountains of that sort here because they were shedding sediments off into the surrounding areas of that age. And so all of these sediments going into the Pacific Ocean had to have been coming from something to the east because there wasn't anything out to the west. So we look at detrital micas, sedimentary mica minerals in the Wildcat Formation over by Rio Del, and they could be chemically traced to the Idaho batholith, which is kind of stunning. How would they get from Idaho to Rio Del? And apparently what that means is there was a river, and ancestral Snake River is the likely candidate, flowing through where the Klamath Mountains are today and spilling out into the ocean where Rio Del is now. Which means that the Klamaths weren't there at that time because the river could come through at that point. So we know during this time period, the present-day Klamaths probably weren't there, at least not in anything like a recognizable form. So it's the rivers that do it, by the way. And so this guy named Diller, back in 1906, he noticed a flatness about the mountains, if you look at it from afar. And he called this the Klamath Mountain peneplain. And it was ridiculed at first, but people have come to realize that this is probably the case. When a peneplain forms, that means that the whole area has been eroded down flat, right down to sea level. And so if you have a peneplain, you know you don't have a mountain because they're the antithesis of each other. So the peneplain formed and it's still visible. Okay. Now the cool thing about it is on top of the peneplain are these various sediment exposures from the Weimar Formation. And they've been dated to 5 million years. And they're sitting on top of this peneplain. So we know that the peneplain was at or below sea level, collecting these Weimar sediments that are 5 million years old, meaning that at least part of the Klamaths weren't there 5 million years ago, which means that in general the Klamaths have emerged in the last 5 million years, the modern day Klamaths. It's a tough one. And what this implies from the general elevations of these sediments now is that they've been rising at this rate per year. And if you add all this up, it adds all up to something like 6,000 feet in that 5 million years, which is a pretty realistic figure for the types of peaks we see in the Klamath these days. So this is probably largely the real story of how recently the modern day Klamaths have arrived. What time is it? 12 after?
What about the
Ha! We're gonna go to 12, we're gonna go to 20 after, is that a problem?
Yeah.
Okay, you, feel free to leave if it's too much for you. Okay,
Great.
so, late Pleistocene, oops, let's go back. Late Pleistocene, this is what the Earth looked like at that time, around 19,000 years ago. This is kind of a significant age for this, the rest of the story here. So, by the time we get to here, you know, in the 5 million years prior to that, the mountains have risen and risen and risen. They might have gotten quite a bit higher than they are now, maybe not. It's just hard to say, because they do know that there's been thousands of cubic miles of sediment eroded off of them since then, just based upon the present topography. 19,000 years ago. That's when the last of the Ice Age was at its peak in the Klamath Mountains, and this is in the Trinity Alps. And these are all the classic symbols of glaciation. This is Emerald and Sapphire Lake, the classic U-shaped valley, the classic glacial lakes, and the classic glaciated peaks around it. Glacial polish up near Caribou Lakes, glacial polish up here near Lake Anna. Lots of glacial evidence, and this is all like day before yesterday. So a modern analog of this kind of stuff. These are glaciers up in Alaska, valley glaciers. The Klamath Mountains would have looked somewhat like this 19,000 years ago. And here's Stewart's Fork again. That opening picture was taken from like right up here, looking down in this direction. And there's all these moraines in there, which tell us that's where the glacier advanced to. So it probably looked very much like this through there, just 19,000 years ago. And to me, it makes me feel like, I like to use this analogy because it feels right. It's like we've walked into the theater just in time to see the credits roll. We've missed the story, you know? And that's kind of like what it is. There's so much cool stuff just happened and we just missed it. Darn it. But there is still a glacial remnant in there. The Grizzly Glacier. Here's the moraine that it has made, and it's up above Grizzly Lake. And here's another moraine. This is the Athabasca Glacier off to the right, and the moraine across from this. So these were modern analogs. And this is a moraine up on the trail going up to Bear Lake. And so they're hard to photograph because they're all forested over now, but if you look close, you can see that they're a mound like this, and they're forested, but all the boulders are roundish. Most of them are roundish. And up at Bear Lake, here's where there have been moraines, and then these side things are moraines too. And if you're walking on the trail, you go up here and it crisscrosses back and forth and goes up along this moraine. And that's where I took this picture. It's a steep trail. And so it's during this time that they were painting the cave paintings in Europe. Lascaux and Peshmerel. Cool stuff. Same thing was happening in Europe. So, speaking of caves, they end up being really cool stories, side stories for the kinds of things that were living here during that time, because now we can start getting actual bones. The fossils before are not actual bones for the most part. They've been mineralized and stuff, but you can get the actual bones in some of these caves. So there's Oregon Caves National Monument, there's a bunch of caves in the Marble Mountains, some of them miles long. This is one of the more famous ones. You have to be fairly skilled mountaineer to get down in there. Samwell Cave and Potter Creek Cave. This is a really cool one, and I'm going to focus on this one next. There's the cave right there. Shasta Caverns. Now, cavern would be the real correct name for limestone caves, but caves has stuck, and that's where we live now. So Samwell Cave is a really cool one, because back in the early 1900s, they still thought that maybe humans evolved on North America. So they were out looking for places where they could find the earliest human fossils easily. And they thought, well, caves are the obvious spot. So a guy from UC Berkeley came here and started excavating, hoping to find ancient human fossils. Here's what it looks like from inside. That's Melinda right there. This is a hard to find cave, but it's easy to get to. It's in the McLeod limestone, and you go up the McLeod, or the McLeod arm of the lake, cruise around to the east side. And it's not signed. It's kind of like this obscure little turnout. You climb down through the baking rock, down around this rugged, and limestone is sharp rock. And so you kind of climb down this rugged thing, and you come upon this place. But the odd thing about it is they found mammoth bones in here, they found mastodon bones, they found this wide variety of Pleistocene megafauna in here. And how the hell they got in here is just beyond me. At that time, the river was probably higher. It's been, this rock is pretty erosive, and the river was probably a lot higher, so and the Ice Age was raging at the time, because they dated all these fossils to between 17 and 24,000 years. So that was right at the peak of the Ice Age in the Klamath. So these creatures were walking probably much closer along the riverbanks and meandered up here. I don't know exactly how a mammoth got in there, except that probably the rocks have been falling off all along, and the cave opening used to be bigger. There I am in comparison to the size, you can see everything. So today is International Sloth Day, by the way. There's a three-toed sloth. The reason why I bring this up is because it's International Sloth Day, but also because they found 2 species of sloth in that same cave. Giant ground sloths, the Shasta ground sloth. Now this is just an artist's representation of it. We don't know how it would have really fleshed out. But the bones are easily recognizable to the expert as sloth bones.
How do they figure the tongue?
Yeah, they have to
Modern
look
day.
at modern sloths and figure, yeah, they must have been something like that. Their skeletal structures are sort of similar. But modern sloths are almost exclusively tree dwellers. And these guys were almost exclusively ground dwellers. And there was some big ones across North America. Here's Therops, and they also found megalonyx in Samwell Cave too. So these are pretty good size, you know, you'd look them in the eye if they were standing in front of you. But there was bigger ones. Legend has it that Thomas Jefferson sent out Lewis and Clark looking for this guy. Jefferson thought they were bringing fossils of it back to Washington, and Jefferson thought they were probably still alive out there. So he sent Lewis and Clark out to bring back a giant ground sloth, but they didn't find it. They just missed it. The credits were rolling when they got there. They also found this thing, the horrific short-faced bear, the most fierce bear of all bears, the killer bear, the horrific, just terrible, terrible, it was a vegetarian, by the way. Based upon isotopes in its bones, it ate largely plant matter. But that was the apparent size of it. They'd be a tough one to deal with.
It's a lot of blueberries.
Yes, largest bear, no. That was in Samuel Cave. This was in Samuel Cave, the shrub ox. That's the actual fossil they found of it. So a very close relative of the musk ox. But, you know, how many of you have ever heard of a shrub ox? Yeah, I'd never heard of one either until I started reading up on Samuel Cave. And these guys were wandering around here. In fact, I found a bone down on the Mad River that I believe is shrub ox.
Wow.
Yeah, it's fossilized. But I took it to museums and looked around and brought it to the HSU. The dinosaur specialist came to HSU a few years ago. I handed it to him and said, "Tell me this is T-Rex." And he said, "That's a mammal, get out of here." I looked at it at the Hall of Mammals in the Natural History Museum in New York and looked online for all this stuff. Finally, I learned that it was likely the bone I had was a scapula with the blade broken off. It was just the joint where it went into the shoulder. And so I started looking for Pleistocene scapula online, and it was pretty much a dead ringer for this guy. This was right over on the Mad River. So the mammoths they found there were the Columbian mammoth, the woolly mammoth in blue, Columbian mammoth in red. These were the largest of the mammoths. So largest of the mammoth crawling into that cave. Go figure. And then this list of other guys. Giant jaguar, mastodon, dire wolf, camels, horses, peccaries, giant condors. If you could think of a condor as giant, you kind of think of a condor as giant anyway, but there was bigger ones. And they went into this cave. And they died there and all their bones were there. But included in that cave were innumerable smaller mammals, some of them still in existence today. There was even things like beavers and lots and lots and lots of mammals, all buried in this assemblage of fossils. Another interesting thing that they found in there, the local Samwell means holy or sacred place because the Wintu Indians went there for sacred rites and stuff. Turns out they have this legend about a young maiden who went into the cave and never came back out. And so when you climb into this opening, it's a drop-off. So you have to rappel down to get further into the cave. And the first person to rappel down found a young woman's bones at the bottom of the cave. And so this was an ancient legend amongst the Wintu, that there she was. And of course right next to her was the skeleton of a mountain lion that had also had the same fate. So they pulled her bones up and they buried her in the local Indian cemetery. So then, lastly, mining in the Klamath. We think of this as this wonderful era of adventure and opportunity. Not so much. It was pretty horrific. They used these monitors, this is up along Highway 299, to spray water out on here and wash all this sediment out that had gold in it. And all the slurry went down into the sluice boxes where they got the gold out. All the sediment went and filled up the river channels. This water came from Emerald and Sapphire Lakes, where the dams still remain there, and they had it piped, I think it was 24 miles around to get to this location. Here's some of the gold bricks they got. Here's some of the banditos that are just getting ready to steal it. Here's what it looked like shortly after there, and they figured there was 200 feet of sediment. And here's, I climbed up the hillside to try to, with the picture, trying to get the same spot. And here it is today, and they're mining that gravel today to use in aggregate and stuff.
I've heard it's also, that they're also extracting gold from that site. Do you know if that's true or not?
I haven't heard that, but I wouldn't doubt it. They often go back to old gold mines and with modern techniques and extract more gold. They use gold dredging, and here's the gold tailings. You see those all over the place. This is up at Trinity Lake. This is along 299 over by Cave Junction, by Junction City. And this is how they actually did this. They had a floating thing, and they dredged, they dug, spewed it out the back into these piles. And this thing swung back and forth to drop it off, kind of like a backhoe. And inside they had sluice boxes that processed it all and took all the gold out of it. But they ruined the stream in the process. And they ruined the people who lived along the stream in the process. So all these people were strongly affected by this mining. No one ever mentions this. That's why I bring it up, and that's why I brought it up in the book. It's kind of the untold story. They stole their land, they murdered them, they raped them, they pillaged, they took everything they had. And if they managed to hang on and still stay there, who cares? You know, that was their attitude. And they took everything they could and then left these people with a ruined ecology and most of their relatives dead. But fortunately, they're still with us. They were resilient, and enough of them hung on to where they're still a thriving culture.
That's your dad, right?
Oh, really?
Nice.
Really? Which
Yeah.
one? Which one?
This guy.
Here, point. That's a pointer.
Oh, right there.
Nice.
Oh, cool.
Yeah.
Great. So they're right here with us still. They've made it. Thank God. So the good news. Mountains ignore all of our scraping. They just go on and on and on. They've been around for hundreds of millions of years. They're going to be around for hundreds of millions of years. They're going to keep on going. Long after we're gone, the mountains will remain. Earth abides. There you go. That's it, folks. If you can stand it, you can ask some questions. If you can't stand it, you can